This is a walkthrough of an AS Further Maths Specimen paper, Further Pure 1. Question number 1. The variable y satisfies a differential equation d squared y over dx squared is equal to 3 plus 2y squared dy dx. Given that y equals 1.5 and dy dx equals 2 and x equals 1, use the approximation d squared y over dx squared 0 is approximately y sub 1 minus 2 y sub 0 plus y sub minus 1 all over h squared, and dy dx 0 is approximately y sub 1 minus y sub minus 1 over 2h. And with h equal to 0.1, find an estimate for y at x equals 0.9. Now I like to keep myself organised in a table here, so I'll be starting off with r equals 0. Now from the question here, I have my initial values, so they can go straight in the table. So x sub 0 is going to be 1, y sub 0 is 1.5, and dy dx initially is going to be 2. I'm not sure why I didn't write that down, so I'll put 2 there. So let me just add that and put like a little 2 next to that. Yeah, so those initial values can go straight into the table. Now on this one we have a step size of 0.1, but notice that we're trying to find an estimate for y when x is 0.9, not 1.1. So my next value of r is going to be minus 1. I'm taking almost like a step back, and that means I'm trying to find here y sub minus 1. That's what I'm interested in finding at the end. So then I can fill in, working back like a backward step size. This will be 0.9 I'm looking for. So I'm just going to be using this equation here to find my initial value for d squared y over dx squared. So let me write that down. So dx squared d squared y over dx squared at 0 is going to equal to 3 plus 2 y sub 0 squared dy dx at 0. So I can just substitute those values in. So d squared y over dx squared at 0 is going to be 3 plus 2 times y0 squared, so that's 1.5 squared, times by 2, that's my initial value for dy dx. If I work that out, what do I get? It gives me a value of 12, so that can go into my table. Now I'm going to use this approximation here, so d squared y over dx squared at 0, well that's 12, I've got that. So I'm just substituting in, is approximately y1 minus 2y0, so that's 2 times by 1.5, plus y sub minus 1 all over h squared, so that's going to be 0.1 squared. Now because I know that I'm trying to find y sub minus 1, at this stage I'm going to rearrange this to make y1 the subject, so that I then can eliminate it from the second equation when I use that in a moment. So I'll have 12 times by 0.1 squared, that's 0.12, and then I'll also add 2 times 1.5 to both sides, so plus 3, and then we'll have minus y sub minus 1, so I can write that as y1 is approximately 3 plus the 0.12, so that's 3.12 minus y sub minus 1. Okay, so I'm just going to highlight that because I will be using this to substitute into second equation here. Okay, so we have dy dx initially. We have that value here, that's 2. So 2 is approximately y1. Now I'm going to substitute what I just rearranged here. So that's going to be 3.12 minus y sub minus 1. And then minus y sub minus 1. So this bit here in brackets, that's the substitution. All over 2h, so that's 2 times by 0.1. So let's see what we get with this. So if I do 2 times by 2 times by 0.1, that gives me 0.4. And then if I subtract the 3.12 from both sides, that'll be approximately negative 2 lots of y sub minus 1. So from there, y sub minus 1, which is what I want to find, is going to be approximately 0.4 minus 3.12, and that is negative 2.72, and that's going to get divided by negative 2. So I'll get y sub 1 is approximately, divide that by negative 2, and I'll get 1.36. So I'll just finish that off by saying that an estimate for y at x equals 0.9 is 1.36. Question 2. Use algebra to find the exact set of values of x for which 3x over 2 minus x is less than or equal to 2 over x squared minus 4. So the first thing I'm going to do is to take that right hand side and factorise it, but I'm going to factorise it in such a way that I get 2 minus x as a factor. So at the bottom I will have negative 2 minus x, 2 plus x. Without the negative it would be x plus 2, x minus 2, but I want to get this common factor on both sides. So it's over 2 like this. Then I'm going to add this whole expression over here to the other side. So I'll have 3x over 2 minus x plus 2 over 2 minus x, 2 plus x, and that's less than or equal to 0. From there, what I'm going to do is I'll multiply the top and the bottom of this fraction here by 2 plus x, giving like the same denominator as the second fraction, which means I can put them together. So then I will have 3x times by 2 plus x from the first fraction, and then plus 2 from the second fraction, and that's all over this common denominator of 2 minus x, 2 plus x, all less than or equal to 0. I'll multiply out the top, and then what I'll get is 3x squared plus 6x plus 2 over 2 minus x, 2 plus x. It's all less than or equal to 0. So what I'm going to do now is to find the roots of the numerator, this 3x squared plus 6x plus 2. So if I solve that, I'll do that on my calculator. So 3x squared plus 6x plus 2 equal to 0. That gives me negative 3 plus or minus root 3 over 3. And the denominator roots are going to be plus or minus 2. Now I know that when I come to write my set of solutions, plus 2 and minus 2 need to be excluded from my set of solutions, because that would make the denominator equal to 0. But what I'm going to do now is to draw a sketch of both the numerator and the denominator. So first of all, my sketch of the 3x squared plus 6x plus 2. So both of these roots are negative values, so I can see where it's above and then below the axis. So that will tell me when the numerator is positive and when the numerator is negative. And the green graph here represents the 2 minus x, 2 plus x graph, or 4 minus x squared graph. And here you can see again where it's positive and where it's negative, and it crosses the axis at the 2 and the minus 2. Now, either the numerator or the denominator need to be negative for the whole thing, this whole expression, to be negative. Therefore, for the original expression to be true, but not both. So they can't both be negative, or they both can't be positive. So when I look at this sketch here, I'm looking for places where either the numerator, the red graph, is negative, or the green graph is negative. So what I've done, I've highlighted those bits in orange. So basically when x is greater than 2, remember it doesn't include the 2, can't have a negative denominator. When x is less than negative 2, and then between these two values here. And what I need to do now is now to write this as an exact set of values using set notation. So we'll start with the first one over here. So x is a real number, but x is less than, not less than or equal to, less than minus 2. Then we'll go on to the second one. So we need a union because it's basically going to be all three of these. And the middle one here, so this is where x is between these two values, the minus 3 plus or minus root 3 over 3, and it's equal to, because the numerator can be 0 but not the denominator. And then the last one is going to be also union, and x again real number, but this time x is going to be greater than 2 but not equal to 2. So that forms my whole set of solutions. Less than negative 2, between this minus 3 plus or minus root 3 over 3, and x greater than 2. Question 3. The rectangular hyperbola H has Cartesian equation xy equals 15. The distinct points P, 5p, 3 over p, and Q, 5q, 3 over q, lie on H, where p is not equal to 0 and q is not equal to 0. Part A, show that an equation of the tangent to H at P is given by 3x plus 5p squared y is equal to 30p. So the first thing I'm going to do is to take the equation and rearrange it. I don't have to, because I want to differentiate it. So I could actually use implicit, but y is equal to 15 over x, or you could say y is equal to 15x to the power negative 1. So dy dx is going to equal negative 15x to the power minus 2, which I could also write as negative 15 over x squared. I want the gradient at point P, which means the gradient when x is equal to 5. So gradient at P, so then I will just substitute in 5p into the negative 15 over x squared, so it becomes negative 15 over 5p all squared. If I expand the bottom, I'll get 25 over p squared, which then will simplify. If I divide the top and the bottom by 5, I'll get negative 3 over 5p squared. So there's my gradient. I'll now use y minus y1 equals mx minus x1. So y minus, so now I'm using the whole of this coordinate. So my y1 is 3 over p, so y minus 3 over p is equal to m, that's my negative 3 over 5p squared. X minus x1, which is 5p. I'm going to multiply the whole of this by 5p squared to get rid of the fraction. So I'll have 5p squared y minus 15p is equal to negative 3x plus 15p. And then just rearranging it, and that will give me the form that's required. So bring the 3x over, negative 3x to become plus 3x. The 5p squared y stays where it is. And then I add 15p to both sides, so that equals 30p as required. Okay, part B, write down an equation of the tangent to h at q. Now if we compare coordinate p with coordinate q, everything is the same apart from the p has been substituted with the q. So I should be able to take my answer from part A and just replace p with q. That's the only difference. It does say write down, it's only 1 mark, and if you write something down you don't need to do any working, you should be able to just write your answer down. So all I'm going to do is to replace all my p's with q's, and if I do that I'll get 3x plus 5q squared y is equal to 30q. Moving on, the tangent to h at the point P and a tangent to h at the point Q intersect at the point R. Find as single fractions in their simplest form the coordinates of R in terms of P and Q. Okay, so what I need to do is to solve the equations of the two tangents simultaneously and work out their points of intersection. So what I'm going to do is I'm going to take the equation for the tangent to h at P, and I'm going to rearrange it and make x a subject so that I can substitute it into the other equation for the tangent. So rearranging 3x plus 5p squared y is equal to 30p. To make x a subject, I will get x is equal to 30p minus 5p squared y all over 3. And I'm going to substitute this into the second equation here. So then that will become 3 of 30p minus 5p squared y over 3 plus 5q squared y is equal to 30q. So straight away I can see that these 3's are going to cancel out. So that leaves 30p minus 5p squared y plus 5q squared y is equal to 30q. Now I'm going to divide everything by 5. So if I do that, I'll get 6p minus p squared y plus q squared y is equal to 6q. So if I take the p and q terms over to the other side and factorise, I'll get y, and in brackets q squared minus p squared is equal to 6q minus 6p. Then divide both sides by the q squared minus p squared, so I'll have y is equal to 6q minus 6p over q squared minus p squared. Now that's going to be the difference of two squares, isn't it? So that's going to be q plus p and q minus p. Now I can cancel out q minus p from the top and the bottom because I can factorise the top. So that just leaves y is equal to 6 over q plus p. So I can't simplify that anymore. So that's going to be my y coordinate of R. So now I want to take this and use this to find the x coordinate. So to do that, I'm going to substitute this into this equation because it's already rearranged to find x. So x is equal to 30p minus 5p p squared, and then y is going to be 6 over q plus p, and that's all going to be over 3. I can divide everything through by 3, so that means I can get rid of this. That 30 will become 10, and then the 6 here will become 2. Now I want to continue to simplify this. Now I've got this denominator of q plus p, so I'm going to write the 10p also with a denominator of q plus p, which means then I can put the two parts together. So I'll expand the brackets here as well. So that will give me minus 10p squared, and then all of this is over q plus p. Next, if I expand the brackets at the top, I'll get 10pq, then I'll get 10p squared, but then I'll also get minus 10p squared, so that cancels out. So I'm just left with 10pq over q plus p, or p plus q. Now that can't be simplified any further, so that forms the x-coordinate of r. So I guess I could write down my coordinate fully as one thing. So 10pq over qp, comma 6 over q plus p. And then that would be my final answer. The coordinate of r, the point where these two tangents intersect each other. Question 4. With respect to the origin O, the points A, B, C and D have coordinates 369, 157, 238 and 3 plus k, 6, 9 minus k, respectively, where k is a non-zero constant. Part A, show that vector AD is perpendicular to the plane ABC. Now for the plane ABC, I want two non-parallel vectors that are in the plane. So I'm going to find the vectors AB and then the vector AC. So AB, I'll find that, and I'm going to do everything in column form as 1, 5, 7 minus 3, 6, 9. So that gives me the vector minus 2, minus 1, minus 2. And then the vector AC, and so that will be 2, 3, 8 minus 3, 6, 9 again, and that gives me the vector minus 1, minus 3, minus 1. Okay, and they look similar, but they are not parallel, so they're not multiples of each other. So these will do as a start for my two vectors which are non-parallel, which are in this plane. Now I'm also going to work out what the vector AD is, because I want to find out whether this vector is perpendicular to the plane, in other words perpendicular to these two, and to help me do that I'm going to be using a cross product. So the vector AD, that's going to be 3 plus k, 6, 9 minus k, minus 3, 6, 9. And if I do that, I'll get k, 0, and negative k. So I'm now going to find a cross product of the vectors AB and AC. Then I'm going to compare that to AD. And if AD is perpendicular to the cross product of AB and AC, then AD is going to be some sort of multiple of that vector, because by doing a cross product I find a normal to both of these vectors, which is going to be a normal to the plane, or perpendicular to the plane ABC. Okay, so for the cross product, AB is going to be minus 2, minus 1, minus 2, and AC minus 1, minus 3, minus 1. And so that's going to be I, and then minus 1, minus 2, minus 3, minus 1, minus J, and that'll be minus 2, minus 2, minus 1, minus 1, and then plus K, minus 2, minus 1, minus 1, minus 3. Okay, so let's work this out. So negative 1 times by negative 1 is 1 minus, basically it's going to be minus plus 6 or minus 6. So 1 minus 6, that'll give us minus 5i. And then for the second one, I'm going to have 2 minus 2, so that's going to be 0, so 0j. And then here we're going to have 6 minus 1, so it's going to be plus 5k. Okay, so if I wrote that in column, that's going to be minus 5, 0, 5. Now, I notice that if I actually divide all of this by 5 and times it by negative k, I get the vector AD. So it is actually a multiple. Yeah. Take this vector here, divide it by 5, then times or divide it by negative 5, it doesn't really matter, and then multiply it by negative k. Then I'll get this. So I need to write that in words. So since this k0 negative k is equal to negative k over 5, negative 5, 0, 5, that means that AD is perpendicular to the plane. Right, next part. The right triangular prism with face ABC, triangular prism with a face ABC and edge AD, that's its like length, has twice the volume, so twice the volume of the tetrahedron OBCD. In part B, we need to find the possible values of K. Now, I've written these bits down from part A. They may be useful. So we want to find the volume of this triangular prism. And to do that, we want to find the area of that triangle. And we want to times it by its length. Now, the area of the triangle, we can use the cross product to do that. So it's going to be half AB cross AC, okay, because they are two sides of the triangle, and we want to find a modulus of that. So that's the area of the triangle part, and then we want to times it by, so this is times here, not cross, its length, and its length is going to be the length of the vector AD. So if we work through this, we're going to have half, and then the modulus, the size of this cross product, ABAC. Now we've already worked that out. That's negative 5, 0, 5. So negative 5, 0, 5. Okay, so that's the area of the triangle part times by its length, and its length, that's going to be the modulus of the vector, which we have already, AD, K, 0, negative K. So if we work this all out, we got half times by the size of this vector, so that's going to be the square root of 5 squared plus 5 squared, so root 50. Then times by the size of this vector here, and that's going to be k squared plus k squared, 2 squared k squared, so that's going to be the square root of 2k squared. Now if I simplify all of that and do half times 50 times by root 2, that will give me 5, and then I'll get k. Now it's possible k could be negative, so I either want to put a modulus around the whole thing or a modulus just around the k, just in case k is negative. It's not a problem when it's here, but when we square root it, it can be a problem. We want to make sure we've got a positive volume. So the volume of that triangular prism is the modulus of 5k. Okay, let's now move on to the volume of the tetrahedron. the volume of tetrahedron. So that is given by 1/6 of the triple scalar product, or the modulus of the triple scalar product. So now I just replace A, B and C with my three vectors. OB I've put here, OC and OD. Now I've done it this way around because it's probably going to be easier to find the cross product between these vectors rather than one of these vectors and the one that's got K's in. So let's start by working out the cross product between these two. So we have I, J, K, 1, 5, 7, 2, 3, 8. Let's do it the quick way. So I, 5 times 8, 40, minus 21, that's going to be 19, so 19I. And then 8 minus 14, that's going to be minus 6, but there's going to be a minus there anyway, so it becomes plus 6J. And then for K, 1 times 3, 3 minus 5 times 2, so 3 minus 10, so minus 7K. So now I've put that in, I can now work out the dot product between these two vectors. And that will give me 3 times 19, 3 times, or 19 plus times K, so it's going to be 57 plus 19K, and then 6 times 6, so plus 36, and then times this part here by negative 7, so that'll give me negative 63, and then plus 7K. So then all of this in the modular sign here simplifies to 26K plus 30. So dividing everything by 6, I've got here, so this represents the volume of the tetrahedron. So going back to this bit of the question, that the triangular prism is twice the volume of the tetrahedron, so I need to get my tetrahedron and I need to double its volume, and that will be equal to the volume of the prism. So if I times everything inside the modulus by 2, I'll get 26 over 3K plus 10 is equal to the modulus of 5K. Now whenever we've got a modulus equation and we want to solve it, I need to take this modulus sign, replace it with brackets and a plus sign, then replace it with brackets and a negative sign. Now I only need to do it to one of the moduli, because if I did it to both I'd end up cancelling out my answer. There's sort of only really two combinations which we could have, so both sides could be positive or both sides could be negative, they're both the same, or both sides could be opposite side, one positive, one negative, or negative and positive. So by just changing this modulus to a brackets and a negative sign and a brackets and a positive sign, that covers all the combinations. So let's start with the first one, replacing this modulus with brackets and a plus sign. Okay, so that would give us 26 over 3K plus 10 is equal to 5K. Take away 5K from both sides. I will have 11 over 3K is equal to negative 10. And from there, I can work out K by dividing both sides by 11 over 3. And it gives me minus 30 over 11. Okay, so that's one possible value of K. Right, the next thing I'm going to do is replace the modulus with a negative sign and brackets. So I'll get negative and then brackets 26K over 3 plus 10 is equal to 5K. So I'll rearrange this. So if I add 26 over 3K to both sides, that will give me 41 over 3K is equal to, and this here is going to give me negative 10. And this will give me my second value of K. So if I do negative 10 divided by 41 over 3. I get negative 30 over 41, so minus 30 over 41, and that's going to be my second value of K. Question 5. The temperature in a room of a house being regulated by a central heating system was recorded by an engineer every 3 minutes between 8 and 9 on a particular morning. The temperature outside at 8 was recorded as 15 degrees Celsius. Using radians, the engineer modelled the temperature T in the room X minutes after 8 by this equation. T is equal to 119 plus 38 cos X over 3 plus 79 sine X over 3 all over 6 plus 4 sine X over 3 plus 2 cos X over 3. Figure 1, this diagram here, shows the recorded temperatures and a graph resulting from the engineer's model. Using the T substitution, T is equal to tan X over 6, show that the equation can be rewritten as T is equal to 81T squared plus 158T plus 157 all over 4T squared plus 8T plus 8. Okay, so I'll notice that I can think of this angle here like theta over 2, which means that all of these angles here can be thought of as theta. So that means with T equal to tan X over 6, sine X over 3 is equal to 2T over 1T squared, and cos X over 3 is 1 minus T squared over 1 plus T squared. So let's now substitute all of that into our model for the temperature. So we've got 119 plus 38, and then cos X over 3 is going to be 1 minus T squared over 1 plus T squared, and then plus 79 sine X over 3, so that'd be 2T over 1 plus T squared, and then all of that is over 6 plus 4 sine, so that'll be 2T 1 over 1 plus T squared plus 2 cos, so that'd be 1 minus T squared over 1 plus T squared. So all of this needs simplifying down. Let's start with the numerator here and simplify that. So I'll just write down that I'm dealing with the numerator. Now with the numerator, basically what I want to do is to write everything over the same denominator, and that denominator is going to be 1 plus T squared. So I'll have 119 1 plus T squared plus 38 1 minus T squared plus 79 times by 2T all over 1 plus T squared. Let's expand the brackets at the top, so I get 119 plus 119T squared plus 38 minus 38T squared plus 158T all over 1 plus T squared. So simplifying that all down, I get 81T squared plus 158T plus 157 all over 1 plus T squared. Now I've still got some working to do, so what I will do is write that here for my numerator. So 81T squared plus 158T plus 157, and that's all over 1 plus T squared. So let's move on to our denominator now. Okay, so just like before, I want to write everything over the same denominator, so that's going to be 1 plus T squared again. So I've got 6 1 plus T squared plus 4 times by 2T plus 2 times by 1 minus T squared all over this denominator of 1 plus T squared. We'll expand the top, so we've got 6 plus 6T squared plus 8T plus 2 minus 2T squared all over 1 plus T squared. So if we simplify that all out, we'll get 4T squared plus 8T plus 8 all over 1 plus T squared. So I can write down that my denominator is 4t squared plus 8t plus 8 all over 1 plus t squared. So I want to do my numerator divided by my denominator, which is like my numerator times by the reciprocal of my denominator. So that'll be 1 over t squared over, 1 plus t squared over 4t squared plus 8t plus 8. Okay, so what will happen is these will cancel out. So that will give me what they want, 81t squared plus 158t plus 157 over 4t squared plus 8t plus 8 as required. As required. Let's continue. The engineer assumes that while the heating system is switched on, the equation will continue to model the temperature beyond 9 o'clock. Given that the heating systems remain switched on, what we need to do in part B, use our answer to part A to find a proportion of time that the temperature in the room will be above 20 degrees Celsius according to the model. So what we need to do in this part of the question is work out these times here when it hits 20 degrees. Yeah. Now, actually, what we've got is like a little cycle here, haven't we? This is one part of the cycle. So if I can work out the time between this blue cycle here and the time, let's do this in green, here, where it's above 20 degrees, then the green part out of the blue part times 100 will give me the percentage of time that it's above 80 degrees. Okay, so we want to work out what these times here at these points, it will be the same as this cycle continues. So the first thing we're going to do is to say we're going to let t equal to 20. So that means that 81t squared plus 158t plus 157 all over 4t squared plus 8t plus 8 is equal to 20. We'll then multiply both sides by that denominator. So we've got 81t squared plus 158t plus 157 is equal to 80t squared plus 160t plus 160. Right, let's take away 80t squared from both sides, leaving with t squared. Let's take away 160t from both sides. So I'll have minus 2t, and taking away 160 from both sides, we're left with minus 3 is equal to 0. We can solve that by factorising, and I will get t plus 1 and t minus 3. So my values of t are negative 1 and 3. Now t is equal to tan x over 6. So we have tan x over 6 is equal to negative 1. So that will mean that the tan inverse of negative 1 is equal to x over 6. That gives me negative pi over 4 is equal to x over 6. Now this gives me a time when the temperature is 20. However, this is a negative time, and trig equations always have multiple solutions, and this is no different. So I want to find the other solutions, preferably positive, where I get x over 6. So to do that, I don't need a cast diagram. The solutions repeat every pi. So if I keep adding pi to this negative pi over 4, I will get the other solutions. Okay, so I've done a couple more. This should be enough because I'm going to be looking at times, and I also need to solve this other value in a moment. It will be more useful to have these values as decimals. So I do need to realise I've got to times them by 6 first. So I'm going to do that and then write down what the decimal answers are. I'm just going to ignore this first one because that's a negative time. So that gives us 14.137 and 32.987 to 3 decimal places. So I'm now going to do the same with the 3. So I found solutions for the -1. So we'll have tan x over 6 is equal to 3. So we'll start by doing the tan inverse of 3 to give us x over 6. So to 3 decimal places, that gives us 1.249. I want to add pi's to that, multiples of pi, to give me other solutions. So I've got 1.249, add pi to that, I get 4.391, add another pi, 7.532. I now want to multiply these by 6 to find x, and the values of x I get are 7.494, 26.344, 45.193. Now I probably don't need all of these solutions, but it should be enough for me to see what's going on. So I've got 2 solutions here for x and 3 solutions here for x. And what I want to do is I want to go to my graph and I want to fill the times in. Okay, so this first time here at 20 degrees is going to be my first value of x, my lowest value of x, which is this one here, the 7.494. So that's here. So 7.494 minutes. Okay, right. Let's color code it. So that's this one here. So the next biggest value is the 14, which is just here, 14. So that's going to be this time here. So that's going to be the 14.137. So 14.137. Then the next time that it hits 20 degrees, my next biggest value there is the 26. So that's here, so I'll mark that on. And actually this is all I need, the 26.344. So as I said at the start, it's going to be out of this whole cycle, and this part of time between these two, the 7 and the 14, is like the proportion of time that it's above 20 degrees. So I want to do 14.137 minus 7.494 over or out of 26.344 minus 7.494. That's going to be a decimal, times that by 100. Let's see what we get. And that is 35.24 as a proportion. So let's give that as a percentage. So 35.2% above 20 degrees Celsius. Now there may be more straightforward ways of doing it, like actually working out or realizing what the length of one of these cycles are, but this is the way that made sense to me, so that would be my answer for part B. And lastly, part C, give a reason why the equation may not be suitable to model the temperature in the room beyond 9 AM. Now there's lots of different things you can put down for this. My initial thought is that the outside temperature may change, affecting the inside temperature, because the temperature at 8 AM was recorded at 15 degrees. The temperature is likely to change over the course of the day, maybe increase, which means the temperature inside the house is going to be affected. So this model may not continue in this way. We've only got a limited set of data. This is another reason for an hour. Do we know that the model is going to continue like that? Can we extrapolate beyond 9 AM? That might be another reason. There can be all sorts of reasons why it may not be a suitable model. As long as you make a sensible suggestion, you would get a mark for this, but don't give answers like a more accurate value for G. That's one that students like to use, that wouldn't be appropriate here.